Hello, my name is Alexander Peligon. I am a very fresh postdoc at the University of Luxembourg, and today I am presenting my work that I performed during my PhD studies, which is titled 100% code coverage for a third-party Android application. This work is based on the cutting out not executed code, and as a guarantee metric that there is no excess code in the application, we give 100% code coverage. In this talk, I first motivate this work, then I will present two running examples. I will suggest to use dynamic binary shrinking system for testing applications and cutting out the code. Then I will present our approach on cutting the code. Then I will give our result and finally conclude on this presentation. Android is the biggest mobile operating system on the market. It accounts for 86% in market share, with about 2.5 billion of Android devices. Android has its own marketplace where anyone can publish an application and anyone can download this application. And it contains about 3 million of applications published by around 700,000 publishers. These developers are not trustful, and therefore Google needs to verify the applications. Sometimes it even removes such malicious applications. Android unfortunately suffers from vulnerabilities, malware, and targeted attacks. And one of the examples of a targeted attack is a logic bomb. In particular, it can be a time bomb. For example, some malicious attack can be triggered at a specified time, and this functionality could not be tested during the verification process. In more than 10 years of existence of Android, scientific community and industry try to develop sophisticated analysis techniques for security enforcement. However, Android still suffers from malware, and we continue to develop such techniques. One of the recent achievements of Google is that they certified their devices and Android 9 operating system as compliant to common criteria. This means that nowadays Android devices, in particular Pixel 3 and 3 XL, can be used in government institutions and enterprises with strict security policies. However, third-party applications are not the target of this evaluation, but they are often bring the system under the attack. There are different solutions for strengthening the security of Android. Of course, there is a great effort from the Google side to increase the security of Android. For example, they introduce more sophisticated permission mechanism. Then there is an effort from academia. Mostly they work on static analysis. There is great amount of tools. One of them is, for example, a suit that performs static analysis. Of course, we can test manually and automatically and see exact behavior that happened. But in this case, we still have some code that was not executed, and we need somehow to say that it is a benign code and that it will not trigger some malicious behaviors. One of the solutions is sandboxing, which allows to limit behaviors of the application. And the new emergent field in software engineering is called deblotting, which suggests to remove the not used code. And one of the advantages of this approach is also the optimization of application because it becomes smaller. However, there is no approach based on the runtime information for Android, which could remove not executed code or not used code. This work is particularly based on code coverage as a runtime information, and we use ACV tool to generate instruction coverage. This is our previous work, and on this screen you can see the Smiley classes first of all, and the code coverage information that this report produces. On the second image, you can see the exact information that is shown for particular instructions. For example, we can see that these instructions were executed in full. And we use this tool as a precise information for the execution of the instructions. So later we can remove the not executed instructions. In this work, we give two examples. First one is a time bomb application. This is a very simple application that we developed for demonstrating our technique. And the second is a real-life application called Twitter Lite app. And by these examples, we want to first test as much as possible and then look at the code coverage results. Let's take a look in our first example, time bomb application. This is a very simple application which has only one activity. And this activity doesn't do anything. This is a simple page. The only thing that there is a hidden behavior, a time bomb, which works after 22 hours from the build time of the application. And it triggers this small pop-up, which shows that our time is up. For the simplicity, we give two states for this application, and we call them day 0 state, which is the normal running of the application. And the second state is the day 1. This is the state when the time bomb worked. And after it worked, we can see this small pop out. When we take a look into instruction coverage, we see that only 15% covered in total for both states. And for the main package, we can see that about 52% is covered for the day 0, and about 72% is covered for the day 1. In both cases, there is code that was not executed. If we take a look into the source code, which is usually not available for the analysis of third-party applications, but since we wrote this application ourselves, we can demonstrate it. So on the right part, you can see the Java code, but when we analyze the application, we can decompile it and has a representation, in this case, a small representation of the bytecode. And we can see that for both states, there is some code that was executed and some parts of them was not executed. The second example is a Twitter Lite application. This is application is commonly used on the low-end Android devices. It has more than 10 million of installs. And this application is based on the web view component of Android. That means that it actually downloads the web page of Twitter from the internet and then demonstrates it to the user. We can see also that this application is well optimized and obfuscated. It has some debugger checks and collects device information. It also uses some common libraries called RetreFit or HTTP, Crashlytics, Firebase, and JSON. And such architecture is available for different other major applications such as Facebook Messenger, Instagram, and so on. For this application, we performed the following experiment. We first tested it manually for 1 hour, and second, tested it using automated tools, one of them Monkey, second on DroidBot, and finally DroidMate 2. What we can see from this experiment is that all 3 automated testing tools reach around the same code coverage, no more than 15%. But manually we could test more, and this is because automated testing tools could not pass the login page. And when we passed it, of course, we could reach some other functionality. For example, we could take picture and post tweets with this picture, and we could change some settings and so on. But still, even in manual testing, we can see that we tested less than 20% of the code in the application. So what we can conclude from these small examples is that tools or just testing may not trigger well-hidden logic bombs in the applications. And these logic bombs can be malicious. The maximum coverage value is unknown in our experiments. That means that we could not really guide automated tools using code coverage. Excess code still stays never executed, and in our experiments, less than 20% of app code was covered. Therefore, to verify applications, we suggest the dynamic shrinking system. This system allows to test and monitor the application, to explore the behaviors, and finally to cut the application towards the executed code. This shrinking system contains two phases, the exploratory phase and the shrinking phase. So first we need to instrument the application using ACV tool to unlock the code coverage functionality. Then we install it in test and monitor environment. So we can test application, explore some behaviors, and finally we can generate instruction coverage. Then in the shrinking phase, we take the original application and we match it to the instruction coverage that we achieved during the testing. And in such a way, we cut out the not executed code and we get the shrunk application. To cut out the code, we developed a sophisticated approach based on the instructions. In this approach, we remove not executed instructions and not executed methods. This approach is based on basic blocks because it's more convenient to operate with basic blocks when removing the instructions. Then it also takes a look onto conditional logic. For example, if there is an if statement and one branch was not executed, then we can remove not only this branch, but we can remove some if statement and put only the executed branch. Also, we can alter try catch. If the try catch was not executed, we also can remove it. Then we take special attention to synchronized code. Then we remove the not executed switch cases. We also can remove arrays if they were not used during the execution. And finally, we merge gotos in this changed code. Some gotos point to the next instructions, and then they are not useful. Then we can remove static not executed methods. However, we could not remove not static methods because they contribute to the skeleton of the application in terms of object-oriented structure. And these methods we can list as stub methods. Those methods are empty because we remove the instructions from them, and we should not use them for further analysis of application. On this slide, we can see an example of the removal of the code. For example, we can see the declared synchronized close method from the Android framework. And in red, you can see a big amount of instructions that were not executed. And on the right side, we actually removed the not executed instruction. However, we left in place 3 instructions, which, however, would never execute, but we need them. So this code could pass Android runtime verification. We can also mark these instructions as useless, so they would not be counted in our code coverage report. On this example, you can see a method from the time bomb application from the main activity on create method, and we can see that from 95 lines, it goes to 47 lines, so half of the code in the main activity was removed. And when we take a closer look onto the table 1 and showing the results of the shrinking of time bomb application, we can see that there is a significant amount of instructions that was cut out. Then the amount of methods decreased dramatically, the number of classes as well, and the APK size went down only for 12%. This is because most of the place goes for resources. The similar results appear for Twitter Lite application. But in this case, we removed even more instructions and the APK size went down for 28%. To conclude on this work, the large amount of not executed code still stays in the application. Also, the absolute code coverage value is unknown, therefore, we may not guide automated testing tool by code coverage only. Then we demonstrated a viable technique for dynamic shrinking for Android applications. This technique helps to get rid of potentially malicious code, but the disadvantage of this approach is that some legitimate features may disappear if they were not tested during the verification of application. Also, we publish our prototype at the GitHub. For the future work, we consider improvements of the shrinking techniques, because currently this technique works well on these two examples. However, these techniques may fail on some other applications due to the bugs in the tool. Then we would like to bring the dynamic binary shrinking system to life by integrating some analysis tools. For example, some traffic analysis tools, or we could also take a look into Android sensitive APIs. And then we would like to propose a new way to distribute RESTful applications in a shrunk format. And this is all. Thank you.